In this class, we will discuss a problem on computing the effective width and the load carrying capacity of a channel section for a compression member. That means a section will be given here with the specified dimensions, and you are asked to find the compressive load carrying capacity of that particular cold formed steel section. Now here in this example, I am going to consider a section 200 by 80 by 25 by 4 mm. So cold form sections are denoted by these four dimensions. Here you can see that this 200 is the overall depth of the section. 80 mm is the overall width of that flange. Then 25 mm is the overall depth of the lip portion or width, you can say. 4 mm is the thickness. So this 200 is for the web, 80 is for the flange, this 25 is for the lip, and this 4 is for the thickness. So this is how the dimensions of a channel section used in cold form steel design is designated. Now if you want to find out the load carrying capacity, so the formula is effective area multiplied by Fy divided by gamma m, or Fy, or you can take it as Fc also. So that Fc value, of course, in the case of cold form sections, you can see that the value of Fc varies from 230 to 280 Newton per mm square. In this example, he has given 240 Newton per mm square, and gamma m, partial safety factor, is for the material is taken as 1.15. So using this formula, you can find out the load carrying capacity. So here Fc is nothing but Fy here, so 240, and gamma m is 1.15. So that means if you find out this effective area, you can get the value of the load carrying capacity in kilonewtons. Now here, to calculate the effective area, we need to compute the effective width for the different elements of this section. So here you can see that web is one element, these two flanges are elements, and this lip portion is also element. So we can divide this entire section into three elements. So web element, flange element, and lip element. So we have to compute the effective width for all those three elements. Once again, effective width depends on the type of the element, whether it's a stiffened element or an unstiffened element, and the value of local buckling coefficient K we have to calculate based on that. That once again depends on K value depends on whether it is stiffened or unstiffened element. Now first I will take up the web portion. So first thing, we have to compute the effective width of the web. Effective width of the web we have to compute. Overall width he has given 200 in this section. Overall width is 200. If you refer this BS British code 5950, so here 500 is the overall, but actually we have to take 180 mm. 180 mm as the depth of web. Overall depth is 200, but depth of web we have to take 180 mm as per BS 5950. And here on this one, overall width of flange is 80, but we have to take 60. So 60 mm as the what we can say width of the web. Now thickness of course is 4 mm. And coming to the lips, so 25 mm is the overall width of the lip, but we have to consider only 15 mm. So all these details are available in BS 5950 for this particular type of section. Now first I will take up the web portion. So we will calculate the effective width for the web portion. So for calculating that, in the earlier video I have explained about the equations which we have to use for calculating the effective width using this British code. We have to compute a parameter called h, which is given by B2 by B1. So B2 is this 60 and B1 is 180. So that I have explained in the earlier lecture. Please see to that. So here B2 is 60 and this is 180, B1 is 180, ratio is 0.33. We can compute the local buckling coefficient K1 for this web portion. So K1 stands for the web portion, whereas K2 stands for the flange portion. So I have explained all these things in the video. So here K1 is 7 minus 1.8 h divided by 0.15 plus h minus 1.43 h cube. Now if you substitute the value of h as 0.33 and if you simplify, you get the buckling coefficient value for the web as K1 as 5.71. So as per the code, it should be a minimum value of 4 should be there. Suppose that means if the value is less than 4, you have to take 4, but it is greater than 4, therefore we have to consider this value 5.71 as the value of K1. Now we have to compute the critical buckling stress PCR using this formula. Once again, this formula I have explained in the earlier video. It is there in this code. So 185000 K1 into T by T whole square, the value will be in Newton per mm square. So this value if you substitute for K1 as 5.71, T is 4 mm and B is 180 mm for this web. So you get 521.7 Newton per mm square. Now we have to calculate a ratio Fc by PCR into gamma m. Fc is 240 Newton per mm square given. So PCR is this value 521.7 into 1.15 is gamma m value. If you simplify this, you will get 0.4. So this is the limiting value for deciding about the equation to be used to calculate B effective. So since this 0.4 is greater than 0.123, B effective by B is given by this formula as per the code BS code. So this is the formula we have to use. Here in this formula, this value already we know, Fc by PCR gamma m is 0.4. So remaining things if you substitute and simplify, you get 0.983. So this ratio is 0.983. So maximum value is 1. So it is 0.983. So therefore B effective by B is 0.983 or B effective is 0.983 into B. So with B is here once again 180. So if you multiply that, you will get this value 176.94 millimeters. This is for the web portion, effective width of web. So out of this 200 mm, effective width is only 176.94 mm. So I have explained earlier that in the case of compression elements, yet not the full length will be considered by the load. That means complete length will not be effective to carry the load. A portion will be ineffective. So this is how. So here whatever you get here be effective this value. So this from the entire web portion, this much, that is 176.94 mm, only this much is effective to carry the load. So that is how we have to calculate for the web. So this web portion is considered as a stiffened element because both the sides it has supports. So that is why these flange will support this side, this flange will support this side. So this web is considered as a stiffened element. So for the stiffened element, so the minimum value of that K1, you according to the code, it is 4, but it is greater than 4, therefore you have to consider this value. Now coming to the flange portion, the flange portion is also considered as stiffened element because it is supported here by the web and here it is supported by the lip. So these two will act as a stiffener. That's why this is also considered as a stiffened element. So same procedure is adopted here. So K2 becomes the local buckling coefficient for the flange. So by knowing K1, you can find out K2 using this formula. Once again, this formula is given in that BS code which I have explained in the earlier lecture. So this is the formula. Here of course T1 and T2, they are the thicknesses of this web to flange. So here it is equal, both are equal to 4 mm, so it becomes 1 here. So if you simplify by substituting K1 value and H value, you are going to get 0.633. But once again, 4 is the minimum because it is a stiffened element. So we have to take this 4 now because 4 should be the minimum. Here 5.71 is greater than 4, therefore you have to take the greater value. Here also the greater value is 4, this value we have to take for K2. So PCR once again is given by 185000. Instead of K1, K2 will come here, T by B whole square. So into 4, so K2 is 4 into thickness is 4, B is 60. 60 we have to take for the, this is the exact dimensions. You can take this as the exact dimensions. So here if you substitute, you will get the value 3289 Newton per mm square. Once again take this ratio FC by PCR into gamma m. So FC is 240, PCR is 3289 into 1.15 is gamma m. If you simplify 0.063 you will get, please see here, this is less than 0.123. Here it is greater than 0.123. You can see here. Greater than 0.123, we have to use this formula. If this ratio is less than 0.123, then as per the code, B effective will be equal to B. So this is very important. So it is 60 mm only. That means entire length. That means this entire what you can say from here to here 60 mm is the effective width. So this is the effective width for flange. This is the effective width for the web. Now coming to the lip portion, these two lips. So here these lips are treated as unstiffened elements because it is supported by only one side, the other side it is free. So as a conservative case, we can take a value of 0.425 as per the code for unstiffened element. K value is 0.425. Calculate PCR using the same formula, 185000 into K is 0.425 into T by B for the lip. For the lip thickness is 4 and this B is 15. Please note this is this value I have to take for B. So if you simplify it 0.037, once again this is less than 0.123. This is the limiting value. Since it is less than 0.123, here also B effective will be equal to B, which is 15 mm. So what I want to say here is the B effective for web portion is 176.94 mm, B effective for the flanges is 60 mm, B effective for the lip is 15 mm. So these are the effective widths. So now when these effective widths are multiplied by the respective thickness, you are going to get the effective area. Once the effective area is known, so you have to multiply that effective area by Fy and divide it by gamma m to get the load carrying capacity. Now let us complete this by having a tabulated in a tabular form. Let us calculate the A effective value by considering all the elements of the section separately. That means web separately, flanges separately, and you have to take that this lips separately, and corners also we have to take separately. That means here it is something like this. So to compute the effective area, what you have to do here is, so this is the section. So we will divide this section into 4 parts. So this is very important step. After calculating all the effective widths, now first I will take this web portion. This is one part. Web portion is one part. Then flange portions. There are 2 flanges here. This is another part. And lip portion. So lip portion is another part. So something like this. So this is the lip portion you can take. So effective width values we have already computed for this. In addition to that, this corner, these 4 corners also we can consider. So because a portion of the corner also may become effective in carrying the load. So now what I mean to say is here, to compute the effective area, to compute A effective, this is very important. So what I will do here is, I will consider all the 4. So web, first I will take web. So web, so actually we got so effective area is given by B effective multiplied by thickness. So in the case of web, we got the B effective value as 176.94. 176.94 into thickness is 4 mm. So if you multiply this, you will get for the web portion 707.8. 707.8 millimeter square. This is the effective area for the web portion. Next, coming to the flanges, there are two flanges here. So 2 times, I will write 2 times 60 into 4. So 60 is the effective width for the flange and 4 is the thickness. So if you simplify this, you will get 480 millimeter square. That is the effective width, effective area for both the flanges. Next, coming to the lips. If you take up the lips, so here it is 2, there are 2 lips here, 1 and 2. So 2 into, so 15 is the effective width, into thickness is once again 4. So this becomes 120 millimeter square. That is the area of the lips. Next, coming to the corners. So actually here, normally this corner, so you will be having a arc of a circle like this. So you have to understand here, so like this. So center line of the corner. Here, this radius will be 1.5 times t for this corner. Like this. This is R. So which is 1.5 into 4 here, 6 mm. So now we have to compute the length. So that length becomes the B effective length for one corner. It will be, you can take it as 6 mm is the radius. You know that. So this is given by R into theta as per trigonometry. So this length is given by, suppose if this is theta, so that length is given by this is B effective R into theta. So R is here 6 mm. 6 mm for the internal one. For the center it becomes 6 plus 2. So it becomes another plus 2, 8 mm, half of thickness. So it becomes then this, the R means you have to take the R to center. So center it becomes 8. To inner it is 6. Up to here it is 6. And another 2 mm we have to add here. So it becomes 8. So 8 into theta is of course 5 by 2, 90 degrees. If you simplify that, you will be getting, I think, 12.56 something. 12.56 mm. Approximately you can take 12.56, and this is B effective for one corner. So there are 4 corners. So 4 into 12.56 into 4 mm is the thickness. Thickness once again it is 4 mm. You are going to get 50.26 I think. So the value here is 16 into 16 into 12.56, which comes out to be 200.96. Okay, 200.96 or 200.96. Okay, millimeter square. Approximately this is the value. Now, if you add all this, the total, that gives your A effective. So this step is very important. You have to consider the section made up of 4 different portions. One for the web, then 2 flanges, and another one lip, then corner. Okay, there are 4 corners, 2 lips, 2 flanges, and 1 web. So if you add all this, that gives the total. So 200.96 plus 120 plus 480 plus 707.8, which comes out to be 1508.76 millimeters square. So this is the effective area you can take. So now 1508.76 millimeter square. Now if you want to calculate the load carrying capacity, of course compressive load. It is compressive load. P is given by A effective into Fy or Fc divided by gamma. So it is 1508.76 into 240 divided by 1.15. This will be in newtons. You can convert it into kilometers. So finally the value will be, so into 240 divided by 1.15. it comes out to be 314.87 kilonewtons. We will get in newtons, that we can convert to kilonewtons. So that is the axial compressive load carrying capacity of this particular cold formed steel section. So this we have done using that BS 5950 code. So if you are using IS code, slight modification will be there. IS 801 and 802, if you follow, slight modification you will get. So I will discuss a problem in the next class using IS 801 and IS 811, how to get the value of the load carrying capacity. So because most of the designers they follow BS code for cold form steel sections. Earlier they were following only that. Now of course slowly we are following this Indian code, because recently it is there is still some more research has to be done. Still it is going on in cold form steel sections. That's why what designers they do is they will compare the results using both IS as well as BS codes, and finally they will give the section. So this is how we have to analyze a cold formed steel section under compression.